Hello and welcome to the channel Understanding.Concepts.Of.Physics. We are starting with a new topic called as kinetic energy, potential energy and total energy of a simple harmonic motion. In case you have not subscribed the channel yet, subscribe the channel, and we have been posting you so many videos on oscillation. You can just check all the videos from the playlist. So let's just begin with kinetic energy, potential energy and total energy. Now in order to derive equations of kinetic, potential and total energy, we are going to assume that there is a body which is going to oscillate between these two extreme positions. Let's say A is the positive extreme and B is the negative extreme. So I have written over here, this is positive and this is the negative extreme. O is the mean position, so I am writing that as O, which is the mean position. Then initially I am assuming that my particle is at P and I am pulling that particle at Q. So the particle is moving a very small distance and that small distance is written as dx. So dx is a very infinitesimally small displacement. And initially when the particle was at P, the displacement was x. So the displacement is always measured from the mean position, and A is amplitude towards the positive side and minus A is the amplitude towards the negative side. So this is what the diagram is all about. You can just click a screenshot if you wish to have the diagram. Now we'll start with first deriving kinetic energy. Kinetic energy is very easy to find out. So kinetic energy basically has a single formula, that is half of mv square, and you just place the value of velocity and you will get kinetic energy. So we have derived velocity as omega root of a square minus x square. I'll put this value over here. So because if it is a square, if you square it and this root will get off. So I'll get, in place of v square, I'll get omega square a square minus x square. So this becomes my one of the forms of kinetic energy. Also note that in one of the previous video I have shown you how omega square is equal to k by m. So I'll just move this m on the other side. So I get m omega square is equal to k. So wherever there is a k or wherever there is a m omega square, I can write k. So m omega square is replaced by k over here. So you get another form of this equation, kinetic energy. So we have this kinetic energy solved as of now. Now we go to potential energy. Now make sure that you should be knowing that potential energy comes from work, and work has two formulas. Work done is equal to force into displacement, that is one, and this formula is basically the main general formula. But when the force is variable, if the force is variable, then what you do is you integrate the small amount of work and you get the full amount of work. That means, in short, if I would like to conclude here, is force can be constant and force can be variable too. And when the force is constant, you apply work done equal to force into displacement and you get the answer. But when the force is variable, you get W is equal to integration f dx. Okay, this is the small conclusion. However, you might have studied in your earlier class where you have understood why we do that thing. Now, so in order to find out potential energy, I'll try to find out work. But as you know that force is equal to minus of kx. This is the equation of in SHM. So force is not a constant. Force is depending on x. That means force is variable in SHM. So we cannot use the direct formula of force into displacement. We'll have to use the integration thing. So first I'll find out the work done. Why? Because this work done will be stored in the form of potential energy. So in order to find out potential energy, I'll find out the work done. So my formula for work done is dW, that is small work done. Because my displacement is small, my work done would be small. dW is equal to force into displacement. Now the reason why it is minus, because you know that in SHM the force and the displacement are always in the opposite direction. So that's the reason why I have taken a minus sign over here. Then in place of F I can write as minus of kx. So F changes to minus of kx. Minus and minus will become plus, and this is kx dx. Now I'll try to integrate this stuff. So integration of dw and integration of kx. The limit goes from 0 to w and the limit goes from 0 to x. Now many people say that Why to integrate from 0 to x when you have this is 0 and this is a? Why not we integrate from 0 to direct till a? Now if you do that, if you integrate from 0 to a, that means you are finding out the work done in going from mean to the extreme position. But I don't want such a very special kind of formula. What I want is, okay, I should be going from mean position to any particular value here, here, here at any point. So at any point if I go, then the displacement is x. That's the reason we are not using a over here and we are using an x over here. Now following is just a part of integration, so you should be knowing integration. K is a constant that is thrown outside in this equation, no change. Integration of dw becomes w, integration of x becomes x square upon 2. So basic integration you should be knowing. Whenever you integrate, the limits move to the right hand side, so limit went to the right side, limit went to the right side. Then how to treat this limit? You put an upper limit but then minus a lower limit. So upper limit is w, so in place of w I have a w, minus in place of w you have a 0, so w minus 0. Okay, as it is, in place of x you put an x, so you get x square by 2, minus in place of x you put a 0 over here, so 0 square upon 2, 0 square upon 2. 0 square upon 2 is 0, so that is gone, and w minus 0 is w. I'm just writing this part, so half of k x square becomes my work done guy equation. Now this work done is stored in the form of potential energy, which is half of kx squared. Now remove this k by using the basic formula of omega square. So omega square is equal to k by m, so k would be equal to m omega square. So put the value of k over here, so I'll get potential energy is equal to half of m omega square a square. So you got two equations for potential energy as well. Now if you are reached this till this point, that total energy is pretty simple. Total energy is just potential plus kinetic. So potential energy plus kinetic energy. Now potential energy is half kx square, so this is that equation, and kinetic energy is half of ka square minus x square. So half nk is constant outside, and what remains is x square plus, here is a square minus x square. Now plus x square and minus x square gets cancelled and you get a square here. So the final equation for total energy is half of k a square, and also again the same thing, omega square is k by m, so I can write k as equal to m omega square. So wherever there is a k I can write as m omega square. So k is replaced by m omega square a square. So in short, we have total 6 equation over here. First is kinetic energy get 2 equations, half of m omega square a square minus x square, then you have half of k a square minus x square, then for potential energy half of k x square, and potential energy half of m omega square x square, and lastly half of k a square for total energy, and total energy is also half of m omega square a square. Now total energy, kinetic energy and potential energy ka topic is not yet over. We are also here to see the dependency on what factors does the total energy depends. Then we also are about to see a graph, how the graph looks like for potential energy, kinetic energy and total energy, and we are also going to see the conservation, how when a particle moves from mean to extreme, how things are going to change, how kinetic, potential and total energy are going to change. So continue with me, and maybe in the next video we will be discussing all the stuffs which is left out. Thank you so much for watching. Have a nice day. All the best. Bye.